Professor Albert Ferrando at the University Politécnica de Valencia and at the IMPA, Instituto de Matemática Pura y Aplicada. And after the experience with us, he went with a Fulbright fellowship at the Colorado School of Mine, where he's working with Professor Lincoln Carroll. Today he's speaking about macroscopic superposition states of code boson in double with orbital degree of freedom. Actually, he has been working, that's a long title, I was waiting for it back. Actually, he has been working in linear and quantum optics, and now he moved to Bose-Einstein condensates in the United States.
I realized that in fact it's double well potential, so it's longer than that. Good afternoon, thanks for coming, thanks for inviting me to this talk. As I said, I'm currently working at Colorado School of Mines, where I enjoy postdoctoral position thanks to the Spanish Ministry of Science and Education and the Fulbright Commission. And well, under this title, there is Bose-Einstein condensates, maybe in some regimes, and in others there is no Bose-Einstein condensate, and this will be underlying all the talk I'm giving today. Okay, we will talk about cold bosons, okay, atoms, in double well potentials, not optical lattices, but only with two sides, two wells. And since we will consider three dimensions for these double wells, we will have the freedom to consider also orbital degrees, or angular momentum to the cycle. Okay, so. Okay, so after these introductions, I will talk about characterize eigenstates and different regimes in 1 and 3 dimensions. This second section, in fact, is a kind of introduction. It's almost a textbook example. And in the fourth section, we will talk about one fancy example of all this work we did in the stationary case. And I will end up with some conclusions. Okay, this is a scheme of the system. We have bosons in a double well potential. Okay, that could be symmetric or a little bit asymmetric. Okay, there can be some tilt. We have first parameter is the number of bosons we have, okay, which will be constant, and these bosons can tunnel between both wells with hopping energy J, or they interact also between themselves with interaction energy U. So we have three main parameters, N, U, and J, that characterize the problem. And depending on the relationship between these three parameters, we have different physical phenomena, as we will see. Also, we have the freedom of selecting the tilt, but this will be important only in the last section of the talk. Okay. Despite the simplicity of this system, it presents very different regimes of parameters, very different phenomena in these regimes, thus justifying the bunch of theoretical approaches to the problem, ranging from mean-field approaches to direct diagonalization of Bose-Hubbard-like Hamiltonians, or the fanciest one nowadays is the multi-configurational Hartree-Fock methods, which is probably the most complete, but also the harder to solve computationally. Okay, roughly we can distinguish two regimes of parameters. The one in which the tunneling dominates, I mean that J is much bigger than NU, but it's called the Josephson regime.
What is J?
J is the tunneling coefficient, the hopping coefficient, characterize one of the two phenomena that are important in this system to the moment, in this section 2, which is the interaction. We will see much more energies later, which is the hopping, the destruction of one, or the hopping only, the tunneling energies of an atom that disappears here and appears here. Okay? And U is interaction. We will characterize them mathematically in a moment. Okay? So
there is no temperature.
No temperature. They are in very low temperatures, and we have only hopping, and we have no fluctuations. So we have this Josephson regime, in which tunneling dominates, and also this Fock regime, in which the interactions are the ones that dominate over the interactions. U is much bigger than J. Okay, in this regime, in the Josephson regime, we find Josephson phenomena, or Josephson-like phenomena, like Josephson oscillation. Josephson oscillations are, if we start with all the atoms in one side, we let the system evolve, they will slots back and forth between both worlds, something like that. These are radio oscillations or the oscillations that are made frequencies. As interaction is increased, mean field approaches predict macroscopic self-trapping. That means that the atoms remain in one of the wells during all the evolution, and in this interaction-dominated regime is where the quantum effects are more and more prevalent. So we are more interested in that regime, but we will talk about all of them. This is an experiment performed in Heidelberg, where you see that in the tunneling-dominated regime you have this tunneling in time, and if you increase the interaction, you have this self-trapping. Okay, we will come back to this picture at the end of the talk. Okay, so we have roughly two regimes: the tunneling-dominated and the interaction-dominated regime. Okay, all the approaches start with this Hamiltonian, the second quantized Hamiltonian. Okay, here everyone has already done one approximation for the interactions between particles. I mean, there is no potential here because we assume that this is a delta. Okay, that is in points one particle interactions. This is the weakly interacting gas. We assume that it's a weakly interacting gas or low density process. Okay? So this is the starting point. Mean field approaches, now what they do is an ansatz. They assume that all particles are in the same state, the same ground state, for example, and substitute this ansatz in here and use a variational approach to arrive to the García-March equation. And you have to assume that all particles are in the same state.
You're supposing that the repulsive interaction.
Yes, well, depending on the sign of this, down this is the scattering length, could be positive or negative. Okay, but normally it's repulsive. But it could be attractive for bosons and also. Okay. So the mean field do these ansatz. The multi-configurational Hartree-Fock methods, what they do is a more general ansatz. They permit the particles to be in different levels and different numbers, so you have different functions, the shape of the function can change, so you end up with a number of equations which are much more complicated to solve, but it's quite more general. So it depends on the regime, you should use one or the other. What we do here is to expand these field operators in terms, well, this is the common approach, this is the introduction to the section, in terms of the single particle eigenfunctions. We take this Hamiltonian, the single particle Hamiltonian. Here we use the eigenfunctions to build up, localize it in one of the worlds or the other world eigenfunctions. So this is to the moment quite common. And we use just two eigenfunctions to expand the field operator. Okay, in terms of the destruction operators. Okay, the D is for dimension. It could be 1, 2, or 3 dimensions, but we have considered 1. And if we substitute this expansion, we can expand this in any basis. We can use this, for example. We end up with a Hubbard-like Hamiltonian, okay, where we have the popping term and the interaction term, and this is the tilt. To the moment it plays no role in here. Okay.
This expansion is good in the regime that you say is dominated by tunneling, or in what regime?
This expansion to the moment is valid in the tunneling in the Josephson regime. It is valid in the Fock regime, but when you increase enough, we will talk about this later. When you increase the interactions, it turns into the not.
Yeah, because the distinction between the two wells in the strong interaction regime is not always so clear.
And also because other levels, other eigenfunctions turn to be relevant to the problem. We will see that exactly which are the regimes in which regimes of parameters where we can assume this.
The UK are complete.
Excuse me?
The UK are complete set of functions.
I have truncated to just in the left and the right, just two modes. This is a two-mode approximation to the moment. Okay?
And delta B is
Delta.
last equation.
This is the asymmetry between both wells, the tilt between both. To the moment, if there is no both. Okay, let's assume that this is equal. Okay, and well, we'll see in the next section that we will use 8 modes in the 3D case. Well, so we can characterize the eigenfunctions of this Hamiltonian. Okay, these are the eigenfunctions. We can characterize them in terms of a Fock basis. Fock basis is vectors which say that you have NL particles in the left world and the rest N minus NL particles in the right world. And you develop these eigenvectors in terms of these vectors using these CNLK coefficients. Okay, these are our expansion for the eigenvectors. For the string Josephson regime, you neglect interactions. J is much bigger than U, or even U is 0. You can demonstrate that these coefficients has this mathematical form. This is a normalization constant. These are mid polynomials, and this is a binomial coefficient. And also for the eigenvalues. This is plotted here. We just diagonalize that, and so the CNLK coefficients. For example, this is the index for the eigenvectors. This is ground state, and more excited. This is the most excited eigenstate. This is a coefficient for the Fock vectors. For example, for 0, it corresponds to the first Fock vector, which has 0 particles in the left world, all particles in the right world. Next one has 1 particle in the left world, n minus 1 in the right world, on and on, to all particles in the left and no particles in the right. And in this direction, we plot the CNL coefficients. So for example, this is the ground state, or this is the 25/30th eigenstate. Okay? Here, this is a slide of this picture. For example, these are the CNL coefficients for the Fock index, and you see that here you have what we call a harmonic oscillator-like behavior. Okay, this is the way the eigenvectors are in the Josephson regime. Okay, they behave as harmonic oscillator. This is the 19th one. This is what we saw, for example, here. Okay. So let's go to the other regime. We consider that there is no tunneling first. If there is no tunneling, this term is not here. This is all diagonal. Do not consider to the moment the tilt. And the eigenvectors are directly the Fock vectors, Fock states. And the eigenvalue is just a fancy way to write this n minus 1. Okay. So in the not tunneling regime or infinite barrier, you have just Fock vectors as eigenvectors. Okay. If you consider a small tunneling term in your Hamiltonian as a perturbating Hamiltonian, you use perturbation theory to find that the eigenvectors now are symmetric and antisymmetric superpositions of these two Fock vectors, okay, with NL particles and the rest in the right, or n minus NL in the left and NL in the right. Okay, and the symmetric and antisymmetric with these eigenvalues plus this splitting. This is the splitting between the eigenvalues of the symmetric and antisymmetric superposition of these two. This number, since this is very small, this number is also very small, and it will be very important in the problem. Okay, so for n particles in the left, this is n0, 0n. This is the famous Nun state, or a macroscopic superposition state, or there's people that like also to call it a Schrödinger cat. Okay, this is the kind of vector you find in the small tunneling regime, or highly interacting regime. This is the same as before in this regime. You have the K vector, your Fock index, and your ground state. The most excited state is 100, 0, superimposed with 0, 100. Okay. Well, this is this is the same, just a slide of the previous part. Okay, this is a kind of introduction. So going from big interactions to small interactions, or less tunneling to more tunneling, you go from this kind of behavior to this oscillator-like. Okay. So let's go to 3D. Okay, this is a surface plot of a 3D potential. We consider in two directions. We consider harmonic potentials. For example, in this one and in this one, we consider harmonic potentials. And in the third direction, we have chosen graphing potential, which fits more or less the experiments, and which is also very interesting for our purposes because it's this is the kind of potential we consider. In this potential, we are going to consider, instead of only 2 modes, we are going to consider 8 modes, which means that we are going to consider 2 levels. Okay, this is the first single particle eigenfunction of our 3-dimensional single particle Hamiltonian. We will have one of these in one well, this in the other well, and in the excited level we have 3 eigenfunctions: 2 with on-site angular momentum, which is this one and this one, the vortex-like, and 1 with another line. Okay? These are numerically calculated eigenfunctions of this potential. Okay. Here we will see that we also can approximate them with spherical harmonics. Okay. This is our second quantized Hamiltonian again. We approximate the potential in one of the directions, in the third direction also, with a harmonic oscillator, harmonic potential, sorry. And we expand our field operators in terms of our eigenfunctions and also three indices, n, l, m. Okay? L, n for the level, L for the angular momentum, and n for the third component of the angular momentum. Okay? For certain regimes, for the high barrier regimes, we can assume that these eigenfunctions are the spherical harmonics. For example, this and this. We have analytical expressions for this.
In which direction are you taking the third component of the angular momentum? In the horizontal one? Or?
The double wall potential is a good question. It's in this direction. So double wall is in this potential. In fact, if you take a look to this picture, we have the harmonic oscillator in this direction, and in fact these, which are numerically distorted, in this direction. This is not spherical, this is distorted a little bit in this direction. So the double wall, the barrier is in here. Okay. This is one, the other, and the third one is in here. Okay.
So the double wall is now a kind of Mexican hat.
No, it's not a Mexican hat. It's like two bubbles. Like two bubbles.
No.
It's exactly like this. You have one in this direction, one in this direction, and the third one in this direction.
So one is symmetrical in this, is symmetrical around the vertical axis.
Well, it's one in this direction and one in that. One is here, one is here.
So
Is it two lobes?
Yes, it's two lobes.
two lobes, they are not connected. They are
No, not connected.
two
It's two
lobes.
lobes.
But they are connected when you have the barrier.
No, they have to jump the barrier.
Yes, that's the jump.
There is no simultaneous.
Tunnel is in this direction. So, well, here you have the commutational relations, and now involves the three numbers, and Ln. And okay, here we will duplicate for n equal 1, so it turns out that for n equal 1, n equal L, so we will consider only L as the level index. Okay, so we have only L. And this is the energies for this case. Well, so we truncate for 8 modes, this 8, 4 here, 4 in the other wall. And we substitute this in our second quantized Hamiltonian, and we have this Hamiltonian. Okay? So it looks very different to the previous one, but it's very similar. The same processes are here. Let's see.
May I ask you, this angular momentum is
On
side.
side.
Is angular momentum with respect to each load?
It's on-site angular momentum. I mean, it's the angular momentum in this well, and you will have also, I mean, you don't have angular momentum for the whole problem. You have a kind of angular momentum for that eigenfunction. Okay?
So it's not really.
It's not the eigenvalue of the operator. It's on-site angular momentum. It's just that the eigenfunction has angular momentum. Okay, so if you start with all particles in this eigenfunction, you have something which has in this well, you have angular momentum, something like starting with a vortex in here that will flip to the well or whatever.
I'm going to have this L, the third component of the momentum is what conserved.
It's L, no, it's N. The third component is N.
So this is what
It's not conserved.
So it's not, you don't have symmetry along the line joining the two worlds. It's not a symmetry actually the problem.
This line,
Yeah. You don't have symmetry, cylindrical symmetry around it.
yes, I think so.
So you have a component of the point where momentum which is conserved.
Now that you say, it's true that this is in this direction, yes, it is. The third component is conserved. The total angular momentum is conserved. The third component in this direction,
So but
it is.
so then this M you're plotting here is not related to the M of the real or the totally conserved.
What? So let's see this. You have here the energy of the levels, just A0 for the bottom level, E1 for the cited level. So this is a term that was not before because we had just one level. So this is only takes account of the energy of the different levels. Okay. Here you have the same term that before, the tunneling, but now depends on L and N. But this is the tunneling between a particle in the bottom level with n equals 0 to the other one in the same eigenfunctions, or a certain particle with L1, N1 to the other one with the same L, N. And this is the interaction before between Ln, Ln, between n, n minus 1. But here you can also have the interaction between different ends. Okay, but this is the interaction term, the same term as before. Okay, just that you can also have the interaction between different ends, as well as here you have interactions between one different ends and 0, 0. Okay. So the different terms, in fact, are these two, which are the interesting ones. Okay. This one describes the hopping of two particles being at the excited level, L equal 1, with n equals 0, to the two particles in the same well with n equal 1, one with n equal 1, and the other with n equal -1. So in the excited level, you can have hopping between 1, 0 to 1, 1 plus 1 minus 1. Okay, this is a kind of coupling term. And, interesting enough, it does not depend on J, but a kind of U-term of interactions. Okay? Here you have the same between the bottom level in the same well, 0 particles, L equals 0, n equals 0, to L equal 1 and n equals 0 minus 1. You destroy two particles down and creates in L equal 1 with n equals 0, or 1 with m equal minus 1 and 1 with m equal plus 1 in the same. Okay, so these are two coupling terms between both levels, which we'll see that they are very important. Okay, and the J, L, M, and the U are defined like here. Okay, you have your eigenfunctions, these are the eigenfunctions we saw before, 0, 0, 1, 0, 1 plus minus 1, your single particle eigenfunction, and also the U with different, this gives the different coefficients, okay, for your eigenfunctions. Once these eigenfunctions are calculated, you calculate the JLN, the ULN, the energy levels difference in energies, and you have your Hamiltonian characterized, and you can solve it. Okay?
What's the physics of V?
Oh, excuse me?
What's the physics of V of R?
V?
V.
V. This is the double potential. This is the potential. Okay? This is the potential. So these, in fact, are eigenfunctions of this Hamiltonian. Okay? Well, to characterize the eigenfunctions in this case, we will use also the Fock basis, but now the Fock basis involves 4 vectors, which has L, M, 0, plus minus 1, plus 1, 0, and 1, 1. Okay? And we develop our eigenvectors in terms of these Fock vectors. So, well, it turns out that provided that the U's are much bigger than the delta E, the difference between two levels is much bigger than the U's, you can solve the eigenvectors, the eigenfunctions, the Hamiltonian at each level for different L, for different N, and just do the direct product of these eigenfunctions. So at the end, you will have, in some regimes, you will have oscillator-like behavior or Fock behavior, or macroscopic superposition behavior, and your solution will be just the multiplication of these different behaviors. So you will have a regime which you have oscillator-like eigenfunctions, you will have a regime, you have Fock behavior. Okay. So let's go a little bit into detail on this. Well, this problem has the advantage.
When you say oscillatory,
yes,
there is no frequency involved.
No, I mean in terms of the coefficients of the expansion of the functions in terms of the Fock basis remains oscillator-like effect. It has many nodes, or it has kind of Gaussian behavior or something like that. Okay. So the advantage of using that potential is that we can have this kind of plane where we can characterize everything by the height of the potential and the coupling term, the J and the BC. So going in that direction, we go to more and more, less and less tunneling, more and more tunneling, more and more interaction, less and less interaction. So a point in this plane, given by some J and some P0, permit me to calculate the JLM, the U's, and the delta E's, so to solve the problem in every point of this space, this plane. Okay. In some regions of this plane, I will have a Josephson behavior. In some others, I will have a Fock behavior, and in some others, I will have crossings. So we'll see we characterize everything in here. For example, to start, I can characterize with this coefficient nu over j0. I can characterize that, for example, this is equal to 10 to minus 1, this coefficient. In this area, I have a Josephson regime. In all this area, I have a Fock regime. So if I calculate eigenvectors in this area, I will find Fock behavior, and if I calculate, I will have here Josephson behavior. This is an example of a diagonalization in this regime, this Josephson regime. Okay, what is this? If you look below this line, okay, what we have here, we have 8 particles. So we have the same picture that before, that for the first 8 particles. So these are the Fock index for all particles in the bottom level and no particle in the side levels. So all particles here are with L equals 0 and M equals 0. Okay, this is the eigenvector, and this is the eigenvector index, and this is the Fock index. How it goes on, the Fock index? The next one is considering one particle in the excited level and the rest in the bottom level. So the particle which is in the excited level for these eigenvectors is in L equal 1, M minus 1. Here is in the eigenfunction with L equal 1, M0, and here with L equal 1, M1. Okay, and so on. The next group will be with 2 particles in the excited, 3 particles, to all particles in the excited level. So this is the way we characterize. We do it analytically. I don't show here. Well, we characterize the eigenvectors in this regime, in the harmonic oscillator-like regime. In this other regime, what we have is a Fock macroscopic superposition of all particles in the bottom level. Here you have one particle in the excited level, and so on to all particles in the excited level with maybe also this kind of behavior. Okay. So here you have superposition of the states with all particles minus 1 in the bottom level and 1 particle in the excited level. Okay, and this is in here. This blue line and this one is because the other two are related to J0 and U0. But I also have a different J and different U for the excited level. And in fact, the Josephson regime, which is characterized for the excited level by this line, is much bigger in the excited level and the Fock regime is much smaller in the excited level. So tunneling is much bigger in the excited level. The J coefficients are much bigger in the excited level. But this is an intermediate point, something like here. And here what we see is that for the particles, all particles in the bottom levels, they have, in a point like this, they have a Fock-like regime. They are like in a Fock-like regime. They are near this regime. Okay. But if you take a look to the eigenstage where you have all particles in the excited level with M equals 0, L equals 1, what you see is that for the excited particles, they behave as harmonic oscillator states. So in here you have mixed states. It's a mixed regime. This of here. Well, so this is not the only thing we want to do. What we do is to really characterize all regimes in here. Next thing that we can do is to find, we have, in here we see that the first 9 eigenvectors, this is 0 to 9, are the ones where all particles are in the bottom level. But if you increase further you find that these eigenvectors could appear in between the first and plus 1 eigenvectors. So since you have expression for these eigenvalues and these eigenvalues, if you find the coefficients for which this eigenvalue is smaller than this one, you will find when you find the first crossing, the regime in which the excited level starts to play a role. This is this criteria. Okay, so for every point in this area, what you find is that there is no eigenvector with particles in the excited level between the first and plus 1. And in here you have the first particle in the excited level between the n plus 1 eigenvectors. The same you can do in the other side and in this line. So in all this area you have this behavior. And you can numerically calculate for points in here, in this area, to find where you have the crossings. Okay? For example, this is a crossing. This is a point just in here, and you find that these eigenvectors are between the first n plus 1 eigenvectors. Okay? Or in the intermediate, you find that this one has a smaller eigenvalue than this one, or in the Fock routine, you have this kind of behavior. Okay, so in this area you don't need, well, you maybe need the second level, but maybe not. Okay, take into account that the mean field approach is valid in the Josephson regime and when you don't consider excited levels. So in this area, more or less. But you can go on and also find when the ground state is a state where you have excited particles in it, in the state. And you find also a criteria for the Josephson and for the Fock regime, which have these two lines. So for points in here, what you find is that the ground state is in fact a state with excited particles and in the opposite. Okay. And you find also the limits of the system, of the model, as you see it should be here, down. So this is the working interacting assumption. And here what you have is that your basis is not really well suited because the barrier height is almost the same size as the difference between levels. Okay? So now crossing is not involving the ground state and crossing is involving the ground state. All crossings are a character of phase transitions. Okay?
So these crossings means that at each well you have atoms which are at the first excited level instead of being
between the in this case between the n+1 excited eigenvector you have this kind of eigenvectors with particles in the excited levels, and in here even the ground state has particles in the excited level.
Yeah, correct.
So maybe in here you don't need to consider, you only consider the ground state, maybe you don't need to consider the excited level, but for sure in here you need to consider that level.
But basically, what fixes if the atom will be at one excited level or not?
Excuse me?
So, physically or in next
physically, this
what
depends.
Is the set that
Yes.
Atom is at an
This
excited
depends
level or the ground level?
in your potential, the height of potential, and the nature of your atoms, the J. Okay? The scattering length. This is related, the J is related with the problem. So we will have an experiment with certain number of certain kind of atoms, certain scattering length, calculate your J, you will calculate your U's, etc. And you have a potential with a barrier height, and with distance between wells, and you will have this number. So in certain experiments, you will be more in the regime or more into the regime. Okay, so you give the lattice, lower well, you give the nature of the atoms, and you know what you have.
Meaning that in that blue region means that the more probable state is the first excited one.
Yes.
But the atom is higher, is it? Or
Excuse me? No, the most probable state will be always the ground state.
ground state.
Yes. You just, in here, you know that the ground state is even excited. Okay? And what you would like also to do, we will be going to, is that in the quantum regime you want to go to be in this regime as if possible in one of the excited regime, in one of the excited eigenvectors, because those are the ones that solve the behavior N001, which is very interesting for quantum purposes, for information.
Okay.
So in fact at the end of the talk we will try to find out how to obtain in an experiment these excited states. So, well, this purple line, I haven't talked about this. This is the first, when the first eigenvalue of the single particle density matrix is not the only one which is relevant. Okay, this is when this has to be not one. So here you have coherent states, here you start to have smaller and smaller states. Okay, and you have a last ingredient in this, which is that in some moment you start to have coupling to excited level. In the ground state, not that they have particles in the excited level. It is coupled to states which are populated at the excited level due to this ULM time that we have in that Hamiltonian. Okay, so this is a criteria where you start to have shadows. We'll see what is it. To this side you start to have shadows, and to this side you don't have. It's not that the state itself involves particles in the excited level, but it is coupled to other states which are excited. Let's see what it looks like. For example, for a point like this horrible thing is the diagonalization. You have here the first fourth, which as always, you have two crossings here and here. For this one, if you plot the coefficients in that direction, you find that you have two big in the eigenvectors, which are n00n, 8008, but you have coupling to two more excited eigenvectors, which are something here, much smaller, which are populated in the excited level. And also even for the ground state, but here is very tiny, this behavior. In a point like that, this is the same excited, this one, I think, And even the ground state, which is that one, if you take a look here, you will see that there is some shadows, some repetition of this in the excited level with practice coefficients. Okay? So to the right of this line, even, no approach that assumes that all particles on the bottom level is well suited. Okay? So this is the whole picture. We have no crossings, first crossing, and crossings involving the ground state, coupling to excited levels, our Josephson regime, and our Fock regime. So in fact, mean field approaches are well suited in here in this triangle. Okay? But what is worse, that when you increase the number of particles, these lines move. And how they move? These two lines move to the left. Here is the evolution of these lines when you increase n. So this area with no crossing is being smaller and smaller. Also this area is being bigger because it's the difference between these two. And evolves like this. This moves to the left. Okay? And this one moves upwards. So this area in which no crossing, no other levels are required, is being smaller and smaller. Thus making the mean field approach normally people say when you have a big number of particles, you can use the mean field approach, but you have to take into account that it's not only the number of particles but also the interactions which are relevant to see if you have a very interacting regime or not. Okay. So, well, this is our picture in 3D, okay? And now we are going to see some effects. Again, in 1D, we are working the 3D effects in the dynamics of this flow. Okay? So let's go back to the 1D Hamiltonian. Now we know it's J, U, and we know that we have a tonally dominated and an interaction dominated. And here we haven't characterized so well the regimes. And let's study what happens if we start with an initial state in which all particles are in the right well. Okay? To characterize this, we will use, among others, the probability of finding NL particles in the left well and the average population of the left well. Okay? So, in this regime, where J is much smaller than U, what we find is that this, the probability of finding 0 particles in the left well and the average population in the left well has a trigonometrical cosinoidal behavior, depending on omega n. Okay, this is a long time. This has nothing to do with the stationary picture we saw before. And this omega n is proportional to this delta E that we found before for the macroscopic superposition states. Okay. Since this is a small number, this is a very big number. The period of oscillation is a very big number. So in this regime, what we find, this is NL, okay, with the cosinoidal effect. And here what we see is the coefficient, the CNLK coefficients along time. We start with all in the right well, and in some moment they jump to the left well, and they come back to the right well. In the Josephson regime, what happens is that one particle moves to the right well, so we go here, then two particles move to the right well, so it's something much more smooth, something like this. Okay, this is the Rabi oscillation of the Josephson oscillations. But in here, all particles remain in the left well, they copy themselves in the left well, and they jump to the other well. In fact, for a quarter of period, what we find is the probability of finding 0 particles in the left well or n particles in the left well is the same, it's 1/2. So for this time, what you have is at the same time all particles in the right well and all particles in the left well. Why is this interesting? Because these superposition states, 0 and 0 and 0, were static solutions which are excited. So you cannot find an oscillating problem. But in here, during evolution, you find that in some moment you have these particles, all in the left and in the right and the center. Okay. What is the problem of this? Okay. That a small deviation around this symmetry potential, as small as this number, will make the stationary states to collapse to Fock vectors. So your eigenvectors with a small asymmetry will be again the Fock vectors, so this is the stationary, tonally suppressed. And also the period is very long. So this makes sense what you find in the experiments. You cannot see, under these circumstances, you cannot see the time between both wells in the highly interacting regime. Okay? the mean field theory stays the same, and people are not interested in watching these somehow entangled states. But the people that do only quantum, they're interested in finding this. So let's see a strategy to finding these superposition states with rational parameters. So let's increase a little bit further the tilt between both wells. Just this is an integer number, could be 1, 2, 0, 3, etc. And what we'll find is that the eigenvectors are again superposition states, but now are not n0, 0n, but n minus p, with p being this number, p, 0n. Okay, this kind of eigenvectors. And the splitting now depends on n, on j over u, but also on p. Okay, so we have again a kind of superposition states. For this, we find that the mean population of the left well is sinusoidal with a period that depends on the splitting between eigenvectors. But now only n minus p particles tunnel between both wells. P particles remain in one of the wells for all time. Okay, it's somehow because you have a tilt which is the same number. So what you find in the numerical experiment is that you have this again, this tunneling between both wells, but only n minus p particles tunnels between wells. And again, at the quarter of period, you find that the probability of finding n particles in the left well and 0 in the right well, and n minus p in the right well is the same. Okay, so you have here this kind of rectangle state you are looking for. Okay, which is very interesting in this routine. But again, a deviation around this resonant tilt will make things to collapse to Fock vectors if it is bigger than this number. That depends now in the splitting between the. So in the symmetric case, what you have is that you have tunneling between wells with a frequency that depends on delta n, delta e, which is the number, and a robustness that depends on this number also. And in the asymmetric case, it depends on the same thing, only n minus p particles tunnel, depending the velocity and the robustness of this number. So which one is bigger? Well, if we consider the division between both of them, we find that the delta E and P is orders of magnitude bigger than delta En. This is only this tau, the equation between both of them. What does this mean? This means that this is the period of the oscillation. For the symmetric case, it grows with n. This is bigger and bigger. And for the asymmetric case, it grows also with n, but you can control it with p, so making it controllable. Okay. In fact, these are experimental numbers for 287 billion atoms, and j over u, or more or less n minus 1. What you have is that if you choose p to be 197, so only as few as 3 particles tunnels between wells, what you have for this tilt, this number of tilt, what you have is that the period is 117 milliseconds, and the deviations as big as these ones, while in the symmetric case, the period was much bigger, and the deviations are much smaller, by 600 of magnitudes. So in this regime, okay, the mean field approaches by certain Rossby-Tails equations, they find macroscopic self-trapping, while in here you have tunneling, and this is what you are looking for, because during the tunneling you can find these entangled states, which are very interesting, but these entangled states are very weak under small imperfections, and in fact you can find them because the period is very long.
Sorry, so here there are only, is it 3 particles or n minus p particles which are tunneling?
Only 3 particles are
3 particles.
3 particles are n minus p. You have 200 particles.
Yeah.
P you choose to be 197. So
it's here and pre-tunneling, and you have superposition of 197 here.
And 3 particles.
On the other side, and
Yes.
this is entangled.
That's in fact, it's 200 0 and 197 and 3 Okay. This is the superposition. Okay, so to conclude, we have completely characterized the eigenvectors and different regimes in 3D and 2D from 1D for the double well, which is very interesting because you can find exactly in this plane where you have the regimes, where the case here ansatz is valid or not. We find that in the Fock regime, a small disk causes the collapse of our starting eigenfunction, so suppressing the tunneling. But properly designing the field, you can find this tunneling between both wells with reasonable parameters. Okay, so thank you for the attention.
Any other questions or comments?
You can show experiments. Is this? You can say something on those experiments from your work?
Well, yes, I can say. These are resonant parameters. I know that people can design this kind of asymmetry by just using a slope, which is a slope, so they have something which is like a square. And people, when I presented this in the last conference, people doing experiments in Toronto and in Rice, they asked me to know more or less the data to do the experiments. So it's quite reasonable for normal experiments.
But what has not been done? I mean, what is? So you're analyzing something that has been done, or
well,
first
because you haven't tried, and second because maybe this is a self-criticism. Maybe when you consider so much particles in one of the wells, you should consider also more levels, because you are going to have lots of particles in here, and maybe these particles in here are coupled to a set of levels. So, in fact, to do this completely, you should consider more levels in your system, more than two. Because you can have this kind. They call it Landau's Hamiltonian between particles in the ground well, in the ground settle in the motor to the well, and settled particles in the well. But to the moment they haven't tried. They didn't try on the series. Also, I don't know if it is very easy to detect in a quarter of period the entangled state. It is not precise.
Sorry, I still don't understand why particles are not all at the lowest level. So
yes.
Is that because you have small temperature, or do you say you have?
Yes, you have your Hamiltonian, which has this J. Plus delta V and Nj. Okay, so you have this takes account for example, n particles and n-1 particles in one well. This is one energy. But here you take account for increment p n particles, for example. So somehow this is like this. A number of particles remains in all times in this well to compensate this term. The particles which are here interacting, to compensate, in fact, they stay in this well to compensate the particles which are not interacting, this term. Do I explain myself?
No, but I was within one well, usually you have particles which are at different energy level, a different entanglement moment.
Yeah.
And I don't understand why all those levels are populated.
Maybe I have been confusing in that because in this last dynamic experiment I haven't used exactly.
Exactly, you haven't. Exactly. So that was actually you didn't need actually the 3D.
No.
Okay.
This is a future work. We are going to do now is to consider this in 3 dimensions.
Okay.
And consider a starting population of only one of the sites.
Yeah, that's fine. And one thing, maybe something for us that work sometimes on dynamical systems, it would be natural for us to include the tilt to be periodically changing.
Yes.
Is that being considered? Or?
Yes, there is some works on some people that consider. In fact, there is a very beautiful works using nonlinear dynamics, considering graphing potential that lead to graphing equations, and in which they consider the movement of the potential periodically. So they have chaotic trajectories and different things which are interesting.
I think something like is it called stochastic response when you have periodical thing. The stochastic or
Yes, noise.
But here you have instead of noise you have tunneling that could play the role of noise. It's something like a stochastic resonance.
Maybe, I'm not sure. I know that they have this chaotic behavior with The dynamical in the same, exactly the same system, only with a little bit of tilt around moving design. The mean field approach is quite beautiful because they go to a phase space in terms of the difference between phase in one of the quantities, one of the world and the other world, and difference between populations in both worlds. And they found they have an area where they have attractors, and in that area they have this tunneling behavior, and another area when they start to, like in oscillator, they start to move with non-bounded phase, and there what they find the macroscopic macroscopic starts. In fact, the beauty of the mean field is that it's so elegant that it's probably. But because I'm not completely sure in place, now we're thinking that you have to be the start tracking also here. And make this
Yes, you pointed some limitation of the mean field, but I didn't quite understand if you use mean field with a fixed single particle basis or you optimize.
No, that's the point in what this is two improvements that we consider resonant Fock methods do. One is to permit the shape of the function to change with n, and then to consider also more.
So you take a fixed basis.
Yes. Normally what they do for arriving to the velocity equation is to fix the shape of the function. It's not let it change.
In principle, you could even allow for symmetry breaking in single particle basis. So even the angular momentum could be.
No, there is approaches in the mean field case. There is approaches where they consider more and more levels. You can consider a basis which is much longer. Okay? There is an opinion from 2006 where they do that. But the problem is that in any case you cannot consider never this kind of macroscopic superposition state you can find in the Fock regime. You cannot see because you assume that everything is coherent. Okay, and everything is more and more bigger, and you have this expected state. Okay. So it's not only that you can consider more levels, but in any case you cannot see the effects that you find in these regimes.
Yes, eventually in this interacting regime, I think the issue.
But yes, there's people who consider on much larger basis and things like that. But in any case, the real good approach is more controversial, where you have all things all together. But probably in 3D you cannot do it in any case because it's too computational ecosystem.
I have a question on, for example, on these scales. I mean, 10 to 600 milliseconds. This is probably more than the life of the universe.
Yeah, that's the reason. It's written here because it's absolutely too.
So that doesn't change.
It makes no sense. No, we never. So that's the contrast you're looking for. But see the previous slide. It's like sandwich of magnitude. This is logarithmic.
Any other question? Just a curiosity. If you have not a double band but just a single harmonic potential, and then you have these 3D configurations, so harmonic, and this duffing, do you still predict some excitation of some modes, and that these kind of things being observed, this n different from 0 things?
Sure, you can use a four-mode approximation, which has one well.
Yes.
If about the duffing potential, because the duffing potential will give you two wells.
This is the standard thing. I was asking if in the experiments it has been observed something with these spatial distributions.
Well, there are vortices but in that case they are populated all in the separate level. In fact, the generation of the spontaneous generation of vortices in certain regimes is one of the things which was very interesting like 6-8 years ago.
But I had the idea that in that system they were steering the system.
They are forcing the system with
while in your case there is no steering. So I was asking if you can observe still something.
I would say that they cannot be mechanical. You will have these things, but you cannot observe them. You see them only
when they move between. Okay. Okay, let's end the speaker again.